Greetings and welcome to Distill. In the previous class, we discussed about energy balance and how to carry out energy balance in different kinds of systems. So we discussed certain problems on that. All right. So with that, let's begin today's class with this problem. This problem came in GATE 2005. All right. A frictionless cylinder piston assembly contains an ideal gas initially with pressure 100 kilopascal, temperature 500 Kelvin, and volume 700 into 10 to the power minus 6 meter cube. Now remember, in any question, when they give you pressure, temperature, and volume, when they give you all the three, then the first step that you should do is calculate the number of moles using the ideal gas equation. So we will do that before we read the entire question. So we know that PV is equal to nRT. Hence, the number of moles are going to be P1 V1 by R T1, right? So pressure is 100 kilopascal. Volume is 700 into 10 to the power minus 6 meter cube. Then R is 8.314 kilojoule per kilomole Kelvin, and temperature is 500 Kelvin. So let's balance the units as well along with the value. So over here we have pressure, that is in kilopascal. We have volume, that is in meter cube. We have R, that is in kilojoule per kilomole Kelvin. And then we have temperature, that is in Kelvin. Now you people would be remembering that kilopascal into meter cube is nothing but kilojoules, right? So we can cancel out this entire thing, and Kelvin gets cancelled here. So we get whatever the value we'll get it in kilomoles. So if we want to calculate it in moles, so we'll simply convert it over here itself. So into 1 kilomole upon 10 to the power 3 moles. All right, so this 10 to the power 3, it will actually get multiplied here. So you will finally get the value as 0.01684 moles. All right, so we've got moles. All right. Now, once we have moles, then we'll read the question further. The system is supplied with 100 joules of heat. So this is our system now. This is our system with a piston cylinder arrangement. Okay. And it is supplied with 100 joules of heat. All right. It is supplied with 100 joules of heat. And the pressure is maintained constant at 100 kilopascal. So it is a constant pressure process. All right, it is a constant pressure process. Keep that in mind. Okay, so when we have a constant pressure process, then all this heat that is transferred, we studied a generalized expression. Heat transferred is equal to the change in enthalpy. It is directly equal to the change in enthalpy. So we are going to use this concept over here in this problem. All right. So now, since we have the heat transferred and enthalpy variation, this is molar enthalpy in joules per mole. So that is 30,000 plus 50 T. So that is H, which is 30,000 plus 50 T. This is in joules per mole. So the total enthalpy would be number of moles into H, that is 0.01684 into 30,000 plus 50 T. So H from here we'll get as 505.2. Write it clearly. So from here H we'll get as 505.2 plus 0.842 T. All right, this is only in joules. All right, this entire thing is only in joules. Now we know dq is equal to dh, so whatever heat is supplied would actually be responsible for changing enthalpy, right? So enthalpy change would be simply 0.842 into delta T, right? It's simple, right? If you differentiate this, with respect to t. So that is going to be 0.842 dt. So instead of dt, I have taken delta t, and in place of delta dh, I have taken delta h. All right, so this is what you're going to get. Delta h is equal to 0.842 into delta t. Okay, now once you have calculated delta h, and that is equal to 100, we know that this is equal to the heat supplied. So from here, we can get delta T, 100 by 0.842. So delta T we get as 118.765 Kelvin. All right, delta T we get as 118.765 Kelvin. Once we have delta T in hand, then we move on to the further part of the question. So this much we've taken out, we've calculated from whatever was given. All right. Now they are asking you to calculate the change in internal energy. So change in internal energy we have already seen in mathematical expression of thermodynamics, that H is equal to U plus PV. Hence, at constant pressure, delta H can be written as delta U plus P delta V at constant pressure. Right. Now, delta H, we have already calculated it as 100 joules, right? Delta H is 100 joules, right? And when we are talking about P delta V, so we can again use the ideal gas equation. PV is equal to nRT, which implies P delta V is equal to nR delta T. All right, so we are going to use this thing here. So we'll get delta H is equal to delta U plus nR delta T. All right, we have number of moles, we have calculated delta T. So we'll get delta U is equal to 100, that is delta H, minus N, that is 0.01684 into delta T, that was 118.765. Okay, so when we solve, we get this as 83.372 joules. That is the change in internal energy. So D part is the correct option. All right, so hope you could solve this problem. This is a very simple problem. Just don't make it lengthy. All right, what some people might do, they might calculate H first, then from that H keeping temperature value over here. This happens, right? Temperature they keep 500, then they calculate enthalpy in the first state. Then they add 100 to it. They calculate enthalpy in the second state. Then they calculate temperature in the second state. Then they get delta T from that. So that would involve so many steps. We have shortened all that into this, just these 3-4 lines, right? So make sure that as short you can make your solution, it would be better. All right, the shorter your solution is, the better you are going to perform. All right, so that was there about this problem. Okay, so today we are going to talk about variable mass systems. All right, so far we have considered all systems with a constant mass. All right, we have said that we have a system, there is some amount of the substance present in the system. We are either heating it, or we are extracting work from it, or we are doing work on it. All right, and that is increasing its internal energy or its enthalpy or something like that. Then we discussed about pressure, temperature, and volume relations of this kind of a system, right? But in all this time when we have dealt with this kind of a system, so what we have seen is that the mass has always been constant in the system, right? Even when we were dealing with thermodynamics of flow process, even in that case, if let's say the fluid is flowing from this pipe, then in that case it has a constant mass flow rate. So at any given point of time, the mass that is present within the system is the same, right? Since it has the same, it has a constant mass flow rate. Therefore, at any given point of time, the mass enclosed within the system would be the same. So even then, we did not discuss really about variable mass systems. So in this lecture, we are going to deal with variable mass systems. So what will happen if mass varies? All right. So all this has been given over here, that what kind of systems we have discussed. And now we are going to take variable mass systems. So over here, I've given an example of a pipeline. All right, pipeline connected to a tank. So let us say this is a pipeline, and over here there is a valve that connects this pipeline to a tank. All right, that connects this pipeline to a tank. All right, this is a tank. Okay, now if I open this valve, all right, if I open this valve, so the mass, the gas from this pipeline, it will start flowing into this tank. All right, so at initial state, if let's say the mass would be m1, then after the gas has flown inside, so now the mass is going to be m1 plus m, where m is the mass of gas that has entered inside. So now the mass is varying. Now it is a variable mass system. All right, so this kind of a system is generally a variable mass system, where something is entering, but it is not leaving the system. All right, where it is not leaving the system, or something is only leaving the system, nothing is entering the system. So in that case, the mass of the system would change. All right, for example, if you're filling air inside a balloon, right? If you're filling air inside a balloon, and in that case also it's a variable mass system. Air is entering the balloon, so that is why the mass of air inside the balloon, it is changing, right? Similarly, if you're inflating a tire, then in that case also it is a variable mass system. So all these kinds of systems are variable mass systems. Here, the amount of gas that is present within the system is not constant. All right, at initial state it is something, final state it is something else. All right, so when we are talking about a variable mass system, we really need to understand certain concepts very properly. All right, so let's say we have a gas inside a rigid tank. All right, we have a gas inside a rigid tank. Then in that case, the gas, it has a property of occupying volume equal to the volume of the container it is stored. We are just taking a case. All right, that there is a gas that is present inside a rigid tank. So in that case, this gas, it is going to have a property of occupying volume equal to the volume of the container it is stored in. Right, that is true. So if this is the container in which I am filling some gas, then the gas molecules would be such that they'll spread themselves into this entire system. Right, no matter how much gas molecules I'm giving, if I give more gas molecules, then they would concentrate themselves. The density of the molecules present in the system would increase, but they'll actually still occupy the same volume, right? They'll spread themselves out. So if I'm storing a gas in a 10-liter container, then whether it is a 5 gram of gas or it is 50 grams of gas, the volume occupied by the gas would always be 10 liter. All right, this is the case of a rigid tank. All right, this is a case of a rigid tank. So in that case, the volume remains constant. It is rigid, therefore the volume is not going to change. So over here, at constant volume, you are adding gas to the tank. All right, you're adding gas to the tank. So this constant volume concept, that irrespective of the mass of the gas added to a rigid system, the volume is going to remain constant. In that case, we would this concept we are going to apply, that the gas is being added at constant volume. So keep this thing in mind, that gas in a rigid tank is added at a constant volume. All right, so keep this in mind. We'll apply this while we'll be solving problems. All right, so when we're talking about variable mass system, then when we're talking about a variable mass system, then so far we have discussed constant mass system where the mass is constant. So over there we discussed that since PV is equal to nRT and N and R are constant because of constant mass system, therefore because of the mass being constant always, so PV by T is going to be constant in general. All right, because we have considered a constant mass system. But now I'm considering a variable mass system. So if my mass is variable, therefore even N is variable. So now only constant left is R. So we'll actually have PV by NT is constant. So therefore, we can form P1 V1 by N1 T1 is equal to P2 V2 by N2 T2. And number of moles can be simply converted into molecular mass, right? Sorry, number of moles can be easily converted into mass, right? So if you multiply the number of moles with the molecular mass on both sides, so you will get the mass of the system. So even this case can be followed. P1 V1 by M1 T1 is equal to P2 by V2 by M2 T2. All right. So both these equations are true for variable mass concepts. All right. So whenever we are dealing with a variable mass system, one equation you can form using the equation of state. All right. One equation can be easily formed using the equation of state. For forming the second equation, we are going to deal with these concepts. So the second equation that we are going to form is generally an energy balance equation. All right. So heat gain, for that, this concept has to be understood, that heat that is gained or lost at constant pressure is enthalpy. All right. Although you people know, but still I'm focusing on this concept once again, that heat gained or lost at constant pressure is enthalpy. Similarly, heat gained or lost at constant volume is internal energy. Okay. And for third concept is that for an insulated system, heat lost is equal to heat gained. All right. Heat lost is equal to heat gained. So using these three concepts, we are actually going to make our equations. All right. We are actually going to make our energy balance equation. So let's see what are we going to do. So let us consider this example. A rigid insulated tank that is initially evacuated is connected through a valve to a supply line that carries steam at 1.2 megapascal and 673 Kelvin. So it carries steam at 1.2 megapascal and 673 Kelvin. Okay, so they have given data for steam tables. All right. Now the valve is opened and steam is allowed to flow slowly into the tank until the pressure reaches 1.2 megapascal. It is actually a common, this is actually a common sense that if steam is flowing into the tank, then it will keep on flowing until both the pressures become same. So now you have to, while you're reading this problem, you have to keep this in mind, that when the pipeline is connected to the tank, when the pipeline is connected to the tank, so the tank is rigid. All right, tank is rigid. So since tank is rigid, therefore here the volume is going to be constant. Okay, the volume is going to be constant. And over here, the pressure is constant. In the pipeline, the pressure is constant. So we are moving our steam from a constant pressure system to a constant volume system. Okay. So what are we doing? We are sending steam from a constant pressure system. We are giving energy output from a constant pressure system, and we are giving energy input from a constant volume system. And this entire system is initially, the entire system is insulated. Therefore, no heat would be lost. Okay. So keep these three things in mind. All right. So now I have taken up these data. So this is saturated steam table and this is superheated steam table. All right. So the pressure is given to be 1.2 megapascal, which is equal to 1200 kilopascal. So when we are talking about 1200 kilopascal, let's go here and see the saturation temperature. So saturation temperature is 188 degrees Celsius. All right. While over here, my temperature is 673 Kelvin, which is equal to 400 degrees Celsius. All right. So that is why the temperature is greater than the saturation temperature. Therefore, we have to move to the superheated steam tables. So in the superheated steam tables, we'll see for pressure equals to 1.2 megapascal and temperature is 673 Kelvin, which is 400 degrees Celsius. So 400 degrees Celsius is this. So in the table of 400 degrees Celsius, we are going to see for this, right? So over here, you can see that we have got these data. So we are more interested towards internal energy and enthalpy right now. So internal energy is 2955.5 kilojoule per kg, and enthalpy is 3261.3 kilojoule per kg. All right, this information is given to us. Okay, now see what is happening in the question. They are saying that we have taken a pipeline, we have connected it to a rigid tank, which is initially evacuated. So here, initially, mass is 0. And then mass is being admitted here from a constant pressure of 1.2 megapascal. When it is being admitted here, then the pressure here is not constant. The pressure in the tank is varying, but in the tank we have volume that is constant. All right. So whenever we are dealing with such a system, always remember we have to take these two separately. So we'll call this pipeline as my system number 1 and my tank as system number 2. So when we talk about system number 1, so in system number 1, you are losing heat. You are sending heat out at constant pressure. All right, you're sending heat out at constant pressure. So this heat that you're sending out is equal to the enthalpy over here. All right, since heat at constant pressure is enthalpy, so this heat that you're sending out, this is actually equal to enthalpy, right? Then when you're taking system number 2, which is your tank, so here you're getting heat in, right? Here you're getting heat in while we are dealing with an energy balance. So when you're getting heat in, and you're getting heat in at constant volume. So whenever you get heat in at constant volume, so that is equal to internal energy, right? So you have to see that Q out is actually in enthalpy of state 1, while Q in is actually in internal energy of state 2, right? So we know enthalpy of state 1 at which the steam is maintained. It is 3261.3 kilojoule per kg. So we know that H1, the heat that is moved out, is H1, which is 3261.3 kilojoule per kg. All right, this is the heat that is moving out. All right, then when we talk about Q in, that is heat in, that is equal to U2. All right, this is next thing. And also, since my entire system is insulated, therefore heat out is going to be equal to heat in. So heat lost by this system 1 is equal to heat gained by system 2. So in that case, your H1 is going to be equal to U2. This is a very important result. H1 is equal to U2. All right. So in general, keep this in mind that whenever we are taking anything from a constant pressure process to a constant volume process, then in that case, the change in internal energy over here is actually equal to the enthalpy that is entering from here. All right, is equal to the enthalpy that is entering over here. So initially over here, there was no internal energy at all because the Mi was 0. Therefore, U would also be 0, right? The net internal energy would be 0. But finally, since there is some mass, so we are going to assume whatever mass it is. So we are not we're not interested in that mass for now. So we'll just say that now it has some internal energy, and that internal energy, when divided by that mass, gives you U2. So you have H1 is equal to U2. So in that case, U2 is equal to 3261.3 kilojoule per kg. All right, keep this in mind. So now in the tank, you have pressure is equal to 1.2 megapascal and you have internal energy of the tank as 3261.3 kilojoule per kg. So in that case, what is the temperature of the tank? So you have to go back and see for the steam tables. At 1.2 megapascal, you have to find a temperature at which internal energy is 3261.3. So if you see the internal energy over here, it is 3123.4, and over here it is 3296.3. Means the temperature is going to be somewhere between 500 and 600. So what we are going to do, we are going to approximate it, right? We are going to approximate it. So for that, remember, you have to use this way. Suppose if suppose if this is my initial, that is my lower limit A, and this is my upper limit B. So my internal energy would be UA and UB. All right. So internal energy is somewhere between UA and UB, and temperature is somewhere between TA and TB. So what we can do, we can estimate the temperature. We'll get an approximate value of temperature. So you get U minus internal energy of lower limit upon U is the internal energy that we are actually finding upon upper limit minus lower limit internal energy. Over here, that is equal to T, where T is the temperature corresponding to this internal energy, minus TA, which is the lower limit temperature, upon TB minus T. So this is a way in which you can approximate your temperature in case you don't have proper sufficient data. So you can even approximate the temperature. All right. So internal energy over here, it is given to be 3261.3. UA is 3123.4. Then UB is 3296.3. And this is 3123.4. Similarly, T we don't know. TA is 500, right? 500. Then TB is 600, and again TA is 500. So from here, you get temperature is equal to 520.243 Kelvin. So this might be somewhere close to what the exact value of temperature is, but yes, this way you can actually approximate the temperature values in order to get the solution problem. All right. So in case you don't have sufficient data available, then this is a way in which you can actually approximate the temperature. So temperature was asked, so it is going to be around 520.243 Kelvin. All right. So that was a quite easy problem. All right. It's quite easy. So now we move on to this example. This is a very interesting example. All right. A rigid tank of volume 0.1 meter cube initially contains a refrigerant at 283 Kelvin. 60% by mass of the refrigerant in the tank is vapor and the rest is liquid. So first of all, they have given us V is equal to 0.1 meter cube. V means volume of the tank, right? Then they have given 60% by mass of the refrigerant is vapor. So what this implies is, this is basically a mixture of vapor and liquid under saturation. So that is why over here, this gives you the quality. So quality, if you remember for steam, we discussed quality is the mass fraction of vapor, right? So mass fraction of vapor over here as well is going to be the quality. That used to be the quality of steam. This is going to be the quality of refrigerant. So X you will get as 0.6. All right. Once you get quality is equal to 0.6, then we have a lot of information with us. All right. So the tank is connected through a valve to a pipeline which carries the same refrigerant at 403 Kelvin and 1 megapascal. So now this is the pipeline. This is the tank. The volume of the tank is 0.1 meter cube. The temperature of the tank is 283 Kelvin. Okay. And even pressure of the tank, since here we have a mixture of partially condensed liquid, partially condensed vapor. So in that case, the pressure is also equal to the saturation pressure at 283 Kelvin. So that is 415.8 kilopascal. 415.8 kilopascal. All right. So once we have the saturation pressure, which is 415.8 kilopascal, over here, we have X, that is quality. So we have information about this tank for now. Then over here, we have pressure as 1 megapascal and temperature is equal to 403 Kelvin. All right. So we have this. Then the valve is opened and the refrigerant is allowed to enter the tank till the pressure in the tank reaches 1.017 megapascal, at which the contents of the vessel is entirely saturated vapor. Now the valve is closed. All right. So determine the mass of refrigerant admitted, the heat transferred, and this is the data given. All right. So first of all, over here we have pipeline at constant pressure. All right. So let us consider the pipeline as our system number A, and let us consider our tank as system number B. Okay, we'll consider tank as system number B. Okay, so now since in the pipeline the pressure is going to remain constant, so we are only interested in enthalpy of the pipeline. So enthalpy at 403 Kelvin and 1 megapascal is 514.69 kilojoule per kg. So specific enthalpy of state of system number A is 514.69. Okay, now then we have specific volume of saturated liquid and vapor at 283 Kelvin, which is 7.94 into 10 to the power minus 4 plus, and this is for liquid, and for vapor we have 4.945 into 10 to the power minus 2 meter cube per kg. So we have specific volume of vapor and liquid. So therefore, can we calculate the specific volume of the gas in system number B? Yes, we can definitely calculate specific volume. So this is my initial state. All right, this is my initial state of the gas. So I'll call this as initial state. So in initial state, this is the tank, this is the temperature, this is the pressure, and this is the quality. All right, this is my initial state. Okay, so in initial state, when I calculate volume, that is the specific volume. So specific volume is going to be the volume of fluid into 1 minus X plus specific volume of saturated vapor into X. All right. So specific volumes are given 7.94 into 10 to the power minus 4 and 4.945 into 10 to the power minus 2. And X is given to be 0.6. So from here, the specific volume comes around 0.03 meter cube per kg. All right. So once you have a specific volume, then you can definitely calculate the mass, which is the volume of the tank upon the specific volume, because all of this gas that has entered, that is present, this is actually occupying the volume of the tank. So that is why mass is going to be 0.1 upon 0.03, which is approximately equal to 3.335 kg. All right, 3.335 kg. That is the mass of the gas in state number 1. So I'll call it M1. And this is V1, this is V1. All right, and this is V2. Okay, so I have got mass in my state number 1. All right, initially when tank was when valve is closed. All right, when valve is closed and no gas has been admitted. Now we'll move to the final state. All right, now we'll move to the final state that I'll call state 2. So in the final state, the tank is connected through hole. the valve is opened and the refrigerant is allowed to enter tank till the pressure reaches 1.017 megapascal. So over here, the pressure is 1.017 megapascal, and temperature is going to be, since over here the contents are all saturated vapor, so you will have the pressure, the temperature is equal to the saturation temperature at 1.017. So that is 313 Kelvin. Okay, this is the saturation temperature. All right, then it is completely saturated vapor. So saturated vapor at 313 Kelvin is 0.02 meter cube per kg. The volume, specific volume is 0. Specific volume 2, 0.02 meter cube per kg. So on the basis of that, when we calculate the mass in state 2, so that is going to be again volume of the tank upon specific volume this time, a specific volume of the gas this time. So that is going to be 0.1 upon 0.02, which is 5 kg. All right. So I guess first part of the problem is solved, that the mass of the refrigerant admitted. The mass of the refrigerant that would be admitted would be the mass that is present in the final state minus the mass that is present in the initial state. This much amount of mass would have been admitted, right? So that is going to be equal to 1.665 kg. So this was quite easy. The mass admitted is 1.665. Now we come to problem that is point number 2. So they have asked us the heat transfer. So heat transferred in this system, to calculate heat transferred, we actually have to see what all energy transfer operations have taken place here. All right. So it is possible that heat would have been added maybe, or it may be possible that it would have been removed. So we are going to assume that heat has been added to the system externally. All right. So when this heat has been added to the system externally, I'll draw it more clearly. So I'll draw it here. All right. So we are going to assume that heat has been added to the tank in order to saturate, to convert it to saturated vapor. All right. This is our assumption. All right. That heat is added. Okay. So now I'll again draw the diagram over here. So this is my pipeline, which is my system number A. From this pipeline, the gas is coming. All right. The gas is coming at constant pressure. All right. The gas is coming at constant pressure. So heat that is coming in from system A is actually the mass of the gas that is coming from the system A. That is basically the mass that has been admitted, right? Into the specific enthalpy in system number A. All right. The specific enthalpy of system A. So mass admitted is 1.665 and specific enthalpy over here it is 1514.69 kilojoule per kg. All right. So this would be the heat that has been coming in from state A. All right, from state number A. So that is 856, not state A, from system A. That is 856.96 kilojoules. All right. So if I consider my tank as my only system now, so this tank, it is receiving heat from here and it is receiving some external heat Q that I have mentioned here. Okay. So this is my system number B, tank is system B. So now I'm going to apply the first law of thermodynamics here. So since tank is receiving heat at constant volume, therefore by first law, we are going to get dq is equal to du at constant volume, right? This is true, right? So we are going to get heat added, that is qa plus q is equal to the change in internal energy of the system. Okay, so change in internal energy of the system. Now, since this is a variable mass system, therefore, it is going to be final internal energy, that is M2 into specific internal energy in state 2 minus M1 into specific internal energy at state 1. So we have to calculate internal energy for state 1 and state 2. Now they have not given in the data about internal energy, right? But they have definitely given us enthalpy. They have given us enthalpy data. And we know that U is equal to H minus PV, right? U is equal to H minus PV, where H is specific enthalpy and V is the specific volume. So once we know that, so therefore we can get U1 is equal to H1 minus P1 into V1, and U2 is equal to H2 minus P2 into V2. All right. Now, P1, as we saw, the initial state was this, where the pressure is 415.8 kilopascal. V1 we already calculated over here, that is 0.03 meter cube per kg. We'll also have to calculate H1 because over in state 1 we have a mixed vapor and liquid. So to calculate H1, I'm going to use the same formula. H1 is equal to X into Hg plus 1 minus X into Hf. And they have given information about Hf and Hg at 23 Kelvin over here. Enthalpy of saturated liquid 213.58, that is Hf, and Hg they have given to be 404.23. So using this data and this formula, I'll get enthalpy at state 1 is equal to 327.97 kilojoule per kg. All right, 327.97 kilojoule per kg. So once I have H1, therefore U1 is going to be 327.97 minus 415.8 into V1, that is 0.03. So U1 you will get as 315.9 0.496 kilojoule per kg. Okay, then U2, so for state 2 you have saturated liquid at saturated vapor at 313 Kelvin. So that is enthalpy of saturated vapor at 313 Kelvin is 419.821. So H2 we have as 419.821. So 419.821. Pressure is 1.017 megapascal, which is equal to 1017 kilopascal. So this is going to be minus 1017 kilopascal into V2 is given to be 0.02 meter cube per kg. Okay, so when we calculate U2, that is going to be 399.481 kilojoule per kg. Now we have U1, we have U2, we have M1, we have M2, right? So we are going to substitute these values, and we also have QA, right? So we are going to substitute all these values. So QA is 856.96 plus Q is equal to M2 that we already have. So we have substituted all these values over here. Okay. So now when we solve, we get heat transfer is equal to this entire thing, right? So that is equal to 88.266 kilojoules. All right, 88.266 kilojoules. So hope you could understand how we solve this problem. This is a very important problem. Correct. This is a very important and very interesting problem. So hope you could clearly understand whatever energy balance we have done, why we have done so. And so this is the example number 2 for you. All right. Okay, so now let's move on to example number 3. This is a very interesting example. And again, very interesting example. And make sure that you do it very carefully while we're solving. All right. So an ideal gas is having a molecular weight of 29. Gamma is 1.4. So gamma is given in this case. Okay, let me read this one. So it is contained in a tank of volume 1 meter cube at 10 megapascal and 400 Kelvin. So number of moles is equal to PV by RT. That is equal to 3.007 kilomole. Pressure was 10 megapascal. That is 1000 kilopascal. Oh, sorry, 10,000 kilopascal. And after that, volume was given and temperature was given. So we have 3.007 kilomole. All right, the gas is discharged into the surrounding atmosphere by opening a valve. All right, so this is present in a tank, and this gas is then discharged into the surrounding atmosphere by opening a valve. All right, so basically the volume is going to remain constant once again to 1 meter cube, right? So now, since this gas is being transferred at constant volume, therefore heat lost from the tank is going to be the change in internal energy. All right. So how to calculate the change in internal energy? So for that, they have given us gamma. All right. They have given us gamma. So gamma is 1.4, which is actually Cp by Cv, right? And we know that Cp minus Cv is equal to R, right? So from here, we can write gamma, which is Cv by Cv, can also be written as Cv plus R by Cv, which is your gamma, right? So from here, you get 1 plus R by Cv is equal to 1.4. All right, 1 plus R by Cv is equal to 1.4. Cv minus Cv. All right, so from here you get R by Cv is equal to 1.4 minus 1, that is 0.4. Therefore, you get Cv is equal to R by 0.4. R is 8.314 kilojoule per kilomole Kelvin. So Cv is going to be 20.785 kilojoule per kilomole Kelvin. And from here, you'll also get Cp, that is Cv plus R, that is 29.099 kilojoule per kilomole Kelvin. All right. So once we have Cp and Cv, then we can move on with the further calculations of a question. So now, since there is no reference temperature given, so we'll take reference temperature as 0 Kelvin. All right, this is the rule. Unless and until they give you a reference temperature, you take it as 0 Kelvin. Okay, so we'll take 0 Kelvin. In that case, the internal energy, initial internal energy, is going to be N1, that is this is N1, initial number of moles, Cv T1. All right, T1 they have given to be 400 Kelvin. All right, so from here you will get N1 Cv T1 as the initial internal energy. And let's say that final state you have N2 moles left after the gas is lost, and then finally when the pressure falls to 5 megapascal, T2 is 5 megapascal. So let's say you have N2 moles, the temperature is T2 and volume is of course the same, right? So now N1 Cv T1 is going to be the initial internal energy, and the final internal energy is going to be N2 Cv T2. All right, you have these two things. All right, then the first equation that you are going to form is the equation of state. All right, you are going to use the equation of state, that is P1 V1 by N1 T1 is equal to P2 V2 by N2 T2. Now, since volume is constant, therefore it is going to be the same. Hence, you'll get N2 T2 is equal to N1 T1 into P2 by P1. P2 is 5, P1 is 10 megapascals. So it is going to be N1 T1 by 2. Keep this as equation number 1. So N2 T2 is equal to N1 T1 by 2. All right. Then we also have internal energies in the initial and final state of the tank, right? So heat lost from the tank is equal to initial internal energy minus final internal energy, that is N1 CV T1 minus N2 CV T2. All right. Then that is equal to the heat that is lost to the atmosphere. Now atmosphere is maintained at a constant pressure of 101.325 kilopascal, that is 1 atm, right? So since it is measured at a constant, it is maintained at constant pressure. This is basically heat lost at constant pressure. So heat gained by the atmosphere at constant pressure is equal to the heat lost, that is N1, number of moles that are lost, that is N1 minus N2, right? If initially N1 moles are there and finally N2 moles are there, and N1 minus N2 moles are sent into the atmosphere. All right. Into, since it is sent as enthalpy, so it is into Cp. All right. Now, initially the moles that are coming out, they'll be coming out at a temperature of T1. Slowly the temperature would increase or decrease to T2, right? So then your temperature, it would slowly go towards T2. So the first mole, it will come out at T1, the second mole will come out at certain different temperature. So overall the moles will come out at an average temperature of T1 plus T2 by 2. This is a very important thing. All right. Since each mole is going to come out between a temperature of T1 and T2, therefore we'll take an average temperature and we'll say that all the moles are coming out at that particular temperature. All right. So on the basis of this, we can form our equations. So from here, we'll take CV common. We'll have N1 T1 and N2 T2. We can write N1 T1 by 2. So minus N1 T1 by 2 is equal to. Now this we are going to solve. So we'll have N1 Cp T1 by 2, no problem. Then minus N2 Cp T1 by 2. Okay. Plus N1 Cp T2 by 2 minus N2 Cp T2 by 2. All right. Now what we'll do is we have two variables. We don't know N2, we don't know T2, right? So from this equation, we are going to substitute either N2 equals to N1 T1 by 2 T2, or we are going to substitute T2. So basically we have to eliminate any one of the two. So I'll eliminate N2. All right. So I'll substitute from this equation. N2 is equal to N1 T1 by 2 T2. So everywhere, wherever I have written N2, I'm going to write this, right? I'm going to write this. So when I simplify this and substitute all the values, so I'll get a quadratic equation in T2. All right, I'll get a quadratic, I'll actually write the simplified form. So that is going to be CV T1 is equal to Cp T1 by 2 plus Cp T2 minus Cp T1 square by 2T2. So this is the simplified form of this equation after substituting N2 equals to N1 T1 by 2T2. So when we'll substitute this and simplify, we'll get this. Okay. So now this, as you can see, when we take LCM, we'll get a quadratic in T2. All right. We'll get a quadratic in T2. So the quadratic equation after substituting the values is 29.099 T2 square minus 2494.2 T2 minus 2327.920. This is the quadratic equation. Okay. Now temperature in Kelvin cannot be negative. So we are going to take the root as minus b plus square root of b square minus 4ac by 2a. We are not going to take minus term. there are two routes, so we are not going to take the negative route. So in that case, we are going to get T2 is equal to 328.93 Kelvin. This is T2. All right. So I think, yeah, they had asked the temperature of the gas. So temperature we have calculated as 328.93 Kelvin. Then you have to calculate the mass discharged. So first of all, let's calculate the moles discharged. Right. So moles discharged is equal to initial moles in the tank minus final moles in the tank. These many moles have been discharged, right? That's what we took. So initial moles are 3.007, final moles are N1 T1 by 2 T2. So N2, I'll write it here. N2 is equal to N1 T1 by 2 into T2. Okay, so your N2 is 1.828 kilomole. Okay, so this is going to be 3.007 minus this. So that comes out to be 1.179 kilomole. All right, these are the moles discharged. Then mass discharged is basically moles into its molecular weight. So it is around 34.191 kg. Okay, that is your answer. Okay, hope you're clear with this. Then we move on to the last problem of this lecture. A tank contains 1 kg steam. This is a a combination. It will contain a tank and a cylinder. All right, tank is losing and cylinder is gaining heat. All right, so tank contains 1 kg steam at a pressure of 2100 kilopascal and a temperature of 648 Kelvin. So this is my tank. The initial state of the tank, which we'll be denoting by 1, is 2100 kilopascal and temperature is 648 Kelvin. And now since since it is a variable mass system, so even mass is going to give you the state value. So 1 kg of steam. Enthalpy and specific volume they have given. So enthalpy is 3192 kilojoule per kg and specific volume is 0.13776. Okay, and also internal energy from enthalpy and specific volume. We can also calculate the internal energy. So internal energy can be H1 minus P1 V1, where V1 is again the specific volume. So internal energy comes out to be 2902.704 kilojoule per kg. All right, this is U1, internal energy. Okay, specific internal energy of state number 1. Okay, so these are all the informations that are given for state 1. Okay, now it is connected through a valve to a vertical cylinder containing a frictionless piston. So through a valve, we have connected this tank to a frictionless cylinder. Okay, this is a frictionless cylinder and it contains a piston. All right, there's a piston over here. All right, so this is a piston. So now the piston is loaded with a weight such that a pressure of 700 kilopascal is necessary to support it. That means that whatever is going to be here, whatever gas is going to be here, the pressure on this gas is always going to be 700 kilopascal. All right, the pressure is always going to be 700 kilopascal. So again, this has become the same system. This is the constant volume system and this is constant pressure system. So heat lost from this is in the form of internal energy and heat gained by this is in the form of enthalpy. All right. So now, initially the piston is at the bottom, the valve is opened, and steam flows into the cylinder until the pressure is uniform throughout the system. All right. So the pressure is uniform throughout the system, and after that, so that means since pressure is uniform, so this pressure is already 700 kilopascal. Since the pressure has to be uniform, so in state 2 we are supposed to have the pressure in the, this is a state for tank only. All right, tank 1, and this is tank in state 2. So in tank in state 2, since the pressure needs to be uniform throughout, so pressure in tank is going to be 700 kilopascal itself. All right, temperature we need to determine. All right, mass let us assume m2. Okay, and no, just a minute, temperature in the tank is given. The valve is slightly open, so the steam flows in the cylinder. The final temperature of steam in the tank is found to be 513. So final temperature is given 513. So the final temperature is given to be 513 Kelvin. All right. So once that is given, M2, we don't know for now. And then they have also given the specific enthalpy and specific volume at this particular point. So H2, they have given us 2933 kilojoule per kg. And V2, they have given as 0.32923 meter cube per kg. All right. So from here, you will get U2 again, H2 minus P2V2. This was P1V1, this is P2V2. So when we solve, we get U2 is equal to 2702.539 kilojoule per kg. This is U2. All right. This is U2. So now, once we have found U2, we have found the initial and final states. Let us apply our equation of state on state 1 and state 2, right? So equation of state, general equation of state for tank gives us P1V1 by M1T1 is equal to P2V2 by M2T2. Since volume of the tank is going to be constant throughout, so we are going to get P1 by M1 T1 is equal to P2 by M2 T2. We have P1, M1, T1, T2 and P2. So from here, we'll get M2, right? So when we calculate, we get M2 as 0.421 kg. Okay, we are going to get 0.421 kg because from here, we'll get M2 as P1, P2 into M1 T1 by P1 into T2. All right. So we'll get this 0.421 kg. That is the mass. All right. Mass of steam in state 2. So M2 we have found as 0.421 kg. Okay. Now, once we have mass, therefore, since heat is lost at constant volume, therefore heat lost by tank is equal to initial internal energy minus final internal energy. So initially mass was 1, internal energy was 2902.704. Final mass is 0.421 and final internal energy is 2702.539. So the heat lost by this tank is equal to 1764.935 kilojoules. All right. So heat gained by the cylinder is basically the enthalpy difference or enthalpy change in the cylinder. So that initially there was nothing in the cylinder and finally there is the steam in the cylinder. So we are going to call it as H only. Instead of delta H, we'll simply call it H. which is 1764.93. All right, mass gained by cylinder, is equal to whatever the mass has been lost by tank. So M1 minus M2. So 1 minus 0.421, that is equal to 0.579 kg. All right. So therefore, specific enthalpy of the cylinder, or basically specific enthalpy of steam in the cylinder, is H upon mass that is gained. So that is 1764.93 upon 0.579. So that is equal to 3048.247 kilojoule per kg. All right, this is the specific enthalpy. So from steam tables, at a pressure of 700 kilopascal and for a specific enthalpy of 3048.247 kilojoule per kg, we get temperature as 565 Kelvin, around 565 Kelvin. So this is the temperature of the steam that is present in the cylinder. All right. So this is how we deal with variable mass systems. So what we basically do is we identify whether heat is transferred at a constant pressure or whether it is transferred at a constant volume. In that case, if it is transferred at constant pressure, then in that case, we find the enthalpy difference. And if it is transferred at constant value, then we find the internal energy difference. All right. And then we do energy balance. If by chance there is some heat or work exchanged, then we include that as well. Otherwise, simply heat lost is equal to heat gain. And then on the basis of that energy balance, we get the results. All right. So let's say if you have a balloon. In the beginning of the class, I gave you an example of a balloon being inflated. So in a balloon, if you fill in air, so this is going to be a constant pressure to a constant pressure transfer. All right. The transfer of mass is going to be from a constant pressure system to another constant pressure system. Over here and over here, the pressure is same, which is equal to 101.325 kilopascal, atmospheric pressure. Because throughout inside the balloon, the pressure that it is going to exert is 101.325 kilopascal. So it's not that complicated system. All right, it is not that complicated system. You simply have to use the equations of state. V1 by M1 T1 is equal to V2 by M2 T, because it is a variable mass system, right? So initially the mass may be anything, whatever is the mass of the air inside initially, and finally whatever it may be, and on the basis of that you can find the temperatures or whatever, right? While we are doing energy balance in this case, then the heat lost is in the form of enthalpy and heat gained is also in the form of enthalpy, because everything is at constant pressure. All right, until and unless there is some external work done, so that has to be taken into account. All right. So anyways, this is how you deal with variable mass system. Hope this video was clear enough.